Okay, so here's a list of functions that you should have covered over the past few years. So in Math 1, you covered linear and exponential, and maybe absolute value as well. Math 2, quadratic, absolute value, step and piecewise. And then here in Math 3, this big list of topics. Okay, so you've sort of learned these one at a time, but in order to be useful, you need to know in which situations each one will apply. So we will want to make sure we remember what each of these things, what each of these functions looks like, and in what situations it would be used. Okay, so if we look at the instructions below, match the graph to the function family that it belongs to and explain how you know. Okay, so we're gonna have to be a little bit careful here. Our explanation has to be specific to that type of function only. Okay, so for example, okay, maybe you recognize this top left one. Okay, you'd say this is, okay, I see this is a linear function. And how do you know that? Or I guess we don't need to. Well, we know that linear functions are just a single straight line. Right, so that's all the explanation we need because, well, there's no other function that's a single straight line, right? You can think about all the other functions we've been through, but linear is the only one that you can describe as a single straight line. Okay, however, this second graph, okay, so you cannot just say, oh, this is a curved graph, because we have a lot of different curved graphs, right? This is curved, this is curved, this has a bunch of curves, right? Curves, right? So here we can't just simply say it's a curved graph. Okay, so what type of function is this? Again, sorry, it's a little blurry on the PDF. But you can maybe tell it's got a vertical asymptote on one end. Okay, and then over here, this is not a horizontal asymptote. It's not flattening out. It is slowly going upward. Okay, so. Okay, so that's the description, right? And again, your description needs to be specific to this graph. So you just look, is there any other graph with a vertical asymptote on one end and it slowly increases in the other? So like this graph down here, bottom middle, has vertical asymptotes, but it has multiple vertical asymptotes and it doesn't increase forever. It has a horizontal asymptote as well. Right, and this one has vertical asymptotes, but again, it's multiple vertical asymptotes and the graph is not increasing forever. All right, so I would say that my description only applies to this one graph, which is what it should always be. Okay, so now looking back at your list of options, maybe someone can remind us what type of function has a graph in which only one end has a single vertical asymptote, while the other end slowly increases forever. Okay, so you can look back through your options. Okay, does anyone think they remember which type of function would have this shape? Yeah, well, maybe you want to skip it and come back then. Right, I believe every function family is used once. Okay, so, well, I'll tell you this one. This one was logarithmic. So this was from Unit 4 this year, end of first semester. Okay, so again, logarithmic is characterized by having a vertical asymptote on one end. If you remember, let's just say log base 2 of x. X cannot be 0, and x cannot be negative, right? Because if x were 0, that's asking 2 to what exponent equals 0, and that's impossible. There's no way for the base of 2 to turn into 0, right? And the input cannot be negative either, right? Because this is asking how do you make the base of 2 into a negative, and again, that's never going to happen, right? So that's why on the graph, there's no inputs in the negatives, and 0 also has no inputs. Okay. All right, so we've done linear, we've done logarithmic. Okay, so go ahead and take a few minutes and see if you can go through the rest of these. Again, make sure you not only write the name of the function, but come up with a description that will help you remember it in the future. Okay, so again, please work on this for a few minutes. remember that we should be not only coming up with the function name, but also like a short description like I've been doing on sort of defining characteristics of that function. You guys maybe another minute to accomplish as much as you're able to. Then you really want to make sure your descriptions apply to only that function. So you can look at your description, look at all the other graphs and see if, oh wait, this description would apply to multiple graphs. If so, try to make it more specific. All right, so again, for these, the type of function, there's no choices there. There's only one correct answer. However, the description can be a little bit flexible, but again, it needs to apply to this graph only. It cannot possibly refer to any of the others. Okay, so the top right one, so this one is a square root function. Okay, and people often mix up logarithmic and square root because you see they both slowly increase on one end. However, the key difference is logarithmic has a vertical asymptote on the other end, while the square root just has a single point. Okay, so that's how you can tell them apart. Oops. Okay, so I said it starts at a single point on one end and it slowly increases in the other end. Okay, so in this case, it increases, right? But you know that if it were like negative square root of x, it would decrease instead, right? So just keep in mind, you know, these descriptions can be affected if there's transformations. Okay, so this one, again, sorry, I guess when it turns into a PDF, it gets kind of blurry, but you should have recognized here that there's multiple evenly spaced vertical asymptotes, right? And then the repeated curved pattern. So first of all, whenever the graph repeats over and over, right, that should be your big hint that this is one of our trigonometric functions, which we just did a few weeks ago. Right, so first I'll say it's periodic, right? So that's a good vocabulary term, which means it repeats over and over. Okay, so, but periodic tells you it's trig, but we've got, you know, 6 trig functions: sine, cosine, secant, cosecant, tangent, cotangent. Okay, so we've got multiple vertical asymptotes. Right, so that rules out sine and cosine because sine and cosine don't have vertical asymptotes. Their denominator is the hypotenuse, which can never be 0. Okay, and then, well, if you remember, well, we'll see it later, but secant and cosecant have the separated upward and downward curves. Here, all the curves are going in the same direction. Okay, so with those pieces of information put together, this can only describe either tangent or cotangent. Okay, so some of you may be thinking, well, I thought it has to be tangent because tangent points this way while cotangent points that way. However, if it were negative cotangent, right, that would flip it upside down to point the correct direction. Okay, so that's why it could be either tangent or cotangent for this one. Okay, so over here we've got this one would be a polynomial function. Okay, so you know, a few things that would help us identify this. First of all, it's a single curve, right? It's continuous. You know, one way you can think of it is you can draw the whole thing without ever lifting up your pencil. Right, there's no vertical asymptotes. There's not 2 separate sections. It's just one continuous graph. Okay, and then I'll say it changes directions multiple times. Right, so here it's going downward. It's decreasing, now it changes direction, now it's increasing, now it's decreasing again, now it's increasing again. Okay, so again, we want to check, well, can this describe any other graph? This one next to it, it is continuous, but it only changes directions once, right? Again, this one's continuous, but it doesn't change direction at all, right? Same with this one, doesn't change direction. Okay, so I guess this one actually does fit the same description, right? It's continuous and it changes direction multiple times. So maybe I should add in another description, not periodic. Okay, so it does not repeat in the same pattern over and over, right? This one repeats in the same pattern over and over. This one doesn't. Okay, so next we've got our quadratic. And this was something you focused a lot on in Math 2. Okay, so there's different ways you can describe the quadratic, right? So it's like a single, okay, so you can say it's a single curve, but that could sort of describe this one also, right? So maybe I'll say the end behavior is the same direction. Because this end goes downward forever, and this end also goes downward forever. You could also mention, if you want, that this is symmetric. Right? Maybe you remember parabolas have an axis of symmetry that cuts the graph perfectly in half, so that you could mirror this half over here. That would be another way of telling it apart from this graph, right? This one is not symmetric. Okay, moving on. This one would be our cube root function. Okay, so first of all, we notice it's curved, right? It's not straight lines. And then it never changes directions, right? It's increasing the whole time. It does have this sort of wiggle in the middle, but it's still, from the left, you're still going upward the whole time. Right, but that also describes this one, right? This is a continuous curve that's going upward the whole time. So we need a way of telling them apart. Okay, so I'll say it's a continuous curve. Okay, and again, for lack of better vocabulary, right, so again, not really an academic term, but I think it's one that you'll understand. Okay, so then over here, we've got a graph which is rapidly increasing on one end, but which flattens out on the other end and actually approaches a horizontal asymptote. It'll never cross this horizontal asymptote. So maybe you recall this from Math 1 as an exponential function. Okay, and then maybe you remember from this year that exponential and logarithmic are inverses, right? So while exponential has a horizontal asymptote, logarithmic has a vertical asymptote. Okay, so again, I'll say that this is a continuous curve with a horizontal asymptote on one end. Okay, so this one over here. So you've got some different things, right? This part is a quadratic, and then these two parts are straight lines. These are linear. So when you've got multiple things happening in the same function, that's called a piecewise function. Okay, so again, you've got, in this case, 3 different pieces, right? That's why it's called piecewise. You're sort of putting different pieces together. Okay, so again, in this case, looks like the x values from 1 down to negative infinity follow one set of rules, 1 to 2 follow a second set of rules, and 2 on follow a third set of rules. Okay, next up, we've got an absolute value function. Okay, so I think this one we can just describe as a V shape. Right, there's no other graph that's shaped like a V. This one sort of shaped the same way, but those are curved, not straight line segments. Okay, so here we've got another periodic function, right? We discussed this earlier. The graph is repeating in the same pattern. But how do we tell this apart from this one and from this one? Well, this is the only one out of the three which is continuous, right? There's no gaps. Okay, so that's how we can tell that this is either sine or cosine. Okay, so this one, this is a step function. And again, you can see it sort of looks like steps, right? If you were to connect these. Okay, so for the step function, you've got multiple horizontal segments. Right, here, 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 and right, every one of these is a step. Okay, so sorry, I guess I was mistaken. This one over here is also piecewise. I thought every function was used only once, but I forgot this one was used twice. So again, this is piecewise. So although every piece is linear, right, each of these three colors is a straight line, they're following different linear functions, right? This one has a positive slope, this one has a slope of 0, this one has a different positive slope. Okay, so over here, this one is a rational function, which you may recall from Unit 2 in first semester. Okay, so remember, rational functions, have a numerator and a denominator. So because we have a denominator, you can divide by 0, which is what creates the vertical asymptotes. And in this case, we also have a horizontal asymptote. Okay, so it's kind of tricky because rational functions don't have to have multiple vertical or horizontal asymptotes. But if they do, then you know it's rational. Okay, and then lastly, so here we've got a periodic graph, right? This is repeated over here, and then, it would continue going in that pattern. So we know it's a trig function, and there's only one left, but, if we didn't know that, right, what sets this apart from sine and cosine? Well, first of all, it's not continuous, right? It's got multiple vertical asymptotes. And then I would also say, well, how do we tell this apart from tangent, cotangent? Right, with tangent and cotangent, the curves are all doing the same thing. While here, half the curves are opening up and half the curves are opening down. Okay, so I'll say they alternate, they go back and forth. Okay, so this is something you should be prepared to do. Given a graph, you should be able to not only identify the type of function, but also give a clear explanation of how you figured it out. And again, your explanation needs to be specific to that type of function. If you just say, it's curved or it's got a vertical asymptote, that could apply to several functions. So you want to make sure your description is specific enough to only describe that type. Okay, so any questions on this page? Okay, so this next table, it's pretty much the same thing we did here, so we don't need to recopy it. But I do want to remind you of some vocabulary that you may use for our activity later. All right, so one thing we want to talk about are, we've talked about the asymptotes and continuous, but you also might want to talk about maybe the vertex or the vertices of the function. Right, so a vertex is where the graph changes direction. So linear functions have no vertex, right? Because it never changes direction, it just goes upward the whole time. But the quadratic function, right, has a vertex right here. It was going upward, and then after the vertex, it now goes downward. Right, and then the absolute value function also has a vertex. Okay, and we also talked about direction of opening, right? So in this case, the absolute value function opens upward, but you can also have an absolute value function opening downward. Okay, and then you also might want to describe the range of the function, right? What y values are possible. So here the range, it goes downward forever, it goes upward forever, right? So the range would be all real numbers or negative infinity to infinity. On the other hand, the square root function, right? The y values, they start at 0 and then they go upward forever. Right, so this range would be bracket 0 because we do hit 0 and then we go upward forever. On the other hand, this quadratic function, it goes downward forever on both ends. But it looks like it only goes up to, I don't know, maybe that's like 6.5. It's hard to tell from this graph. I think it might actually be 7. I think the numbers are above the line. Okay, and then again, you can also discuss end behavior. So for linear functions, right, the end behavior goes in opposite directions. One end goes up, the other end goes down. For quadratic functions, right, the end behavior is in the same direction. In this case, they're both going down, but they could also both go upward. Okay, so again, you're going to be using these or some of these vocabulary terms today, so that's why I wanted to quickly discuss them. Okay, so we'll come back to the rest of this worksheet in a moment, but we're going to do an online activity next. So if those of you here, if you could go ahead and get a device out, and then let me project the instructions. So here's the instructions. Let me type it in the chat for those at home. Sorry. Okay, so again, this table I already did on the front page. So if you want, you can rewrite it here to have it maybe all in one place. But we want to look at this matching the scenario section. Okay, so here we're given various word problems. Okay, so right now we're not trying to actually solve for a single number, right? We're just asked to figure out what function family, and again, the function families are these things. And then again, an explanation of how you know. Okay, so for example, part A, typical student loan has an interest rate of 3.75%. This means a $20,000 loan paid off over 10 years will end up costing you $28,900. Okay, so again, there's no actual like question here, right? There's no unknown. They're just giving you a bunch of information. But you know, we're trying to think of, well, what type of function is represented here? Okay, so you know, a big hint would be interest. You may remember doing interest problems before, right? So the way interest works is you multiply your current amount of money, right, by the interest rate. And then that tells you your interest, and then you add it. Okay, so I'm not going to do the math, but then after you do your first year's value, then you pay the interest rate again, right? So every year you're multiplying by the interest rate. Okay, so when you multiply over and over, that's going to represent an exponential function. Exponential. Okay, so for this one, we actually do have enough information to represent it, right? You may recall the formula. Right, so you may remember it was R over N and NT when we did it in Unit 4, but here we're just going to do compounded annually. Right, so the P, the principal, 1 plus the interest rate, but you have to convert it from percent form to decimal form. So even though it's got a percent sign, or sorry, even though it's got a decimal point, it's not in decimal form yet because of the percent sign. So the way you convert the percent to decimal is you divide by 100, which is like moving the decimal point twice. Okay, and then T the time, it takes 10 years. Okay, so you know this one was you know, it's a realistic real life situation, right? Most people will have to take out loans at some point in their life, whether it's to pay for college or a car or a house, right? So being aware of the way interest is calculated is definitely something that will be relevant to almost everyone. Okay, so you know, some others of these are a little bit less common, right? Like part B. Again, this was news to me, but apparently there's a quantity called the fetch, which is how much I guess, you know, in the ocean, right? Like the amount of distance that the wind blows. Right. So I guess this one is represented by this function. Right. So the length of the fetch or the speed is found by taking the fetch and cube rooting it. Right, so here they just give you the function, right? So you can see the cube root. but for some of the other functions, it won't be as obvious. All right, so this one, the explanation is kind of silly. Okay, so I'm going to ask you guys to take a few minutes and see if you can come up with the types of functions for the other ones. Again, a lot of these you probably haven't seen an example of it directly in class before. It's kind of hard to find real life situations for some of the functions, but go ahead and give it a try. If you can't figure out one, just skip it and move on, and then I'll go over it at the end. Okay, so again, a lot of these you are probably having trouble with, which is expected, but I think maybe C, E, F, I, and M. All right, so I think maybe these five at least are the most directly related to the ones you've seen during class. Okay, so again, if you haven't already, take a look at C, E, F, I, and M. Again, if you've already done those, then try the others, but I think these five are the most, again, directly related to things you've done in school. Okay, I'll give you another 30 seconds or so. All right, let me go ahead and start to discuss these. So for problem C, I'm guessing a few of you put linear. Maybe you saw the word constant speed. So that's a good idea. Linear functions do have a constant additive rate of change, right? Every step is worth the same amount. However, the reason it's not linear is because of, we're talking about the, when you're talking about a car passing you, you're measuring the, you're really looking at the distance between yourself and the car. Okay, so I guess that wasn't really that clear. So if you put linear, I guess I would accept it for this one. But I intended for it to be absolute value because, let's say you're here and then you've got the car over here, right? So, right now, let's say the distance is, 60 feet, right? Well, when the car gets over here, it's still 60 feet, right? You wouldn't say like, this is negative 60 and this is positive 60. With distance, distance cannot be negative, right? You never say the store is negative 2 miles away. It's, either 2 miles north or south or so on. All right, so for this one, again, the intent was absolute value, but if you put linear, again, I would accept it because the wording wasn't as clear. I didn't mention the distance. Okay, problem D. Most years we actually do an example involving these. This year, because of our schedule, we didn't have time for it. But the idea was, okay, so if there's a lot of rabbits and not that many foxes, well, then the foxes are going to be able to eat a lot of rabbits, right? So the foxes have a lot of food, so there can be more of them born, right? But if there is a lot of foxes eating the rabbits, right? So now the numbers of rabbits decrease, right? So as the number of foxes continues to go up, okay, again, there's fewer and fewer rabbits because they're getting eaten. But at some point, right, once there's not that many rabbits left, now the foxes don't have much food. So now the foxes, unfortunately begin to starve, right? So now there's fewer foxes, it goes down. But now that there's fewer foxes, more rabbits can survive. But again, now when there's a lot of rabbits and not that many foxes, all of the foxes have enough to eat, so now there's more of them, right? So it's forming a sine or cosine graph because, again, it'll hit a maximum and then it'll go downward, then it'll hit a minimum and go upward and so on. Okay, letter E. So you've got an initial fee, right? So that's a one-time cost. And then you've also got a constant rate of change. So this one would definitely, this one would be linear. Again, some of you may have put step. So again, in that case, I guess it depends. If you take it for half a minute, do they charge you the full minute or do they charge you only half of the minute, right? So I actually don't know the way the app works. So I guess, again, either one would be acceptable. And again, you've got a constant rate of change. Right, so whether it's the first minute or the third minute or the 10th minute, every minute is costing the same amount. Okay, F, this one would be piecewise, right? Because depending on your situation, you are charged differently. Okay, so G was kind of a stretch, but if you think about the, sort of a shape of roller coaster, right? It's got like little hills and like, dips and valleys. right? So the idea was that, well, the shape is sort of like a polynomial function. So that's the shape of a general track. pH. So if you've taken any sort of chemistry, maybe you're familiar with pH. It describes sort of like how acidic a compound is. So the pH scale is logarithmic. It is not linear. So what that means is that if something has a pH of 2, it's not twice as acidic as a pH of 1, right? Even though 2 is double 1, it's actually 10 times more acidic because the pH, the logarithmic scale, we know is like log base 10. Okay, letter I. Okay, so here, this would be a step function, and more specifically, a step ceiling. Right, because you wouldn't, the store is not going to sell you half a pizza or 1/4 of a pizza, right? So let's pretend you had 9 people at your party. Okay, so if you did 9 divided by 4, that would equal 2.25. But again, the store is not going to sell you 2.25 pizzas, right? So what do? Well, if you round down, if you only have 2 pizzas, that's not enough, right? So it's better in this case to round up. Okay, so as a reminder, the ceiling function says you round up to the next number. Even though 2.25 is closer to rounding down to 2, if it's a ceiling function, you always round up. Okay, letter J. Again, if any of you end up going into like electrical engineering, maybe you'll see something like this. But the key phrase was sum of the reciprocal. Okay, so here you see the value of 80. So the reciprocal will be 1/80. All right, then you've got like 1/100, 1/50. Or if you didn't know a value, it might be like 1/x. Okay, so this you can see represents a rational function, right? Rational because you've got a numerator, you've got a denominator. Okay, letter K. So we're dealing with a circle, right? So area equals pi r squared for a circle. But we want to find out about the radius, right? So we want to solve for the radius. Okay, so to get the radius by itself, you would have to square root both sides. Okay, so since we square root, that's going to make it a square root function. Okay, distance and direction of the shadow of a tree. All right, so if the sun's over here, right, the shadow would be like over here. All right, so when we talk about distance and direction, we're looking at sort of the angle that is formed. Okay, so, for this situation, for this triangle that's formed, what could you measure? Well, you could measure the length of the shadow pretty easily, right? And you could also measure the height of the tree relatively easily. You probably can't measure this diagonal, right? Because that's like floating in the air. It's not an actual object, it's diagonal, right? So if you have the opposite and adjacent sides, you would probably use either tangent or cotangent. Okay, and then lastly, letter M. So here we're throwing a ball into the air. So, anything that's thrown into the air is called a projectile. So projectile motion is described with a quadratic function. Okay, so again, I expect that you had a lot of trouble with these word problems. That's again, that's completely reasonable. this will be something we continue to focus on throughout the unit. Okay, so for the remainder of class, I'll be letting the in-person students see their tests. Those of you online may log off and you can see your test tomorrow. Okay, those of you here